Hello everybody, welcome back. So this is where we left off last time. We were discussing, we had started on the topic of Reynolds transport theorem, and we had started discussing the 1D Leibniz theorem and its three-dimensional extension. And I had said we'll go this way to understand how Reynolds transport theorem works. But for the time being, I want to take a different approach. And the reason is I have realized, if it were a classroom setting, we would be face to face, and I'd be so sure that whether you're getting what I'm talking about, and we have so much better, more ample opportunities to clear doubts than in this particular setting where I'm recording it at just by myself, and I have to guess what questions are going to come in your mind, and the doubt clearing sessions are probably not enough because not everybody is obviously coming to those. Anyway, the point being that there is one more way of understanding Reynolds transport theorem, and take that first because I want to make sure that this idea of control volume and control system stays with you well, and then we can move on to we can discuss the other method of approaching the same thing. So recall, we were discussing that an observer has a choice, and the choice is he can adopt an Eulerian perspective versus a Lagrangian perspective. And often we are interested in the behavior of an entire system of fluid rather than individual particles. And because of that, we decided that the Eulerian approach suits us better, where the observer is now free to choose what we call a control volume, and we'll call it CV for short for the rest of this class. Okay, second. And or you can choose the control system. Now the control system is where you are looking at the fluid particles or the system of particles and following them, and this we had also said is the more natural approach, because this is where the approach in which the original laws are formulated. So F equal to ma applies to this approach. But now that you have an Eulerian approach in which the observer is now free to decide a control volume that is delinked to the system of particles. The control volume can be a window that is fixed in space, it could be moving, it could be deforming, but now the control volume or this window of ours is delinked from the set of particles, and that creates a problem for us. And it is here that the Reynolds transport theorem becomes important, because it's a tool that will allow us to convert from a system point of view to a control volume point of view. Okay. So to start, let us consider an arbitrary control volume. Okay. So I'm just going to draw an arbitrary control volume at time t. And what I'm going to do is I have to draw this again. So I'm just going to copy this right now rather than later. Okay, and you know what, I need this one more time. So okay, sorry about that. Okay, maybe I should have just drawn it earlier. It would have saved us some time. Oh, it's the same color, didn't change color. Okay, much better. Okay, so let us say that at time t and I have a control volume drawn in blue here, and I have the system of particles. System means the control system of particles, and there is some fluid which is moving through space. We'll see when we do this through the Leibniz rule that this is actually, we don't need to learn it this way, but for the time being, let us imagine a fluid moving, and let's say this is at time t. So let us consider a system of fluid particles that is coincident, which means it is occupying the same region of space as our control volume at some time t, and that's what we are trying to show here, that the two are coincident with each other, the control volume and the control system. And at time t plus delta t, things have changed a little bit, and of course we are going to look at a limit of this delta t tending to 0. Okay, so the system has moved out a little bit, and the control volume is obviously fixed in space because that's what the control volume is, although it doesn't necessarily have to be that way, but for the time being let's just consider a control volume that is fixed in space. So the control volume is right there and not changing, and you have the system which has now gotten displaced a little bit. So now let us say that there is a transportable property B. Okay, so let us say, okay, let B be a transportable property. That is a property that can be moved from one location to another, and this is an extensive property, and beta be the specific version of that. Okay, so the beta be the corresponding specific quantity. That means that beta is equal to dB by dm. Okay. So if you have a control volume, okay, or you have this system, right, of particles, and that occupies a certain volume. So in this case it is occupying the same volume as the control volume. Then in that case my total beta, total B for my system will be integral of V system. So this is integrated over the volume and beta times rho dV. Okay, where this is the volume. It's not too difficult to see why that is true, is because if you take any arbitrary control volume and you take a small dV volume in there, which is a differential volume, then my beta is equal to my dB by dm as I wrote before, which is the same as dB by rho dV. So my dB is equal to beta rho. Okay. Now which capital B I am calculating will depend upon which volume I am integrating over. So if I am integrating over the system volume, I will end up getting the B system, right, or the total transportable extensive property associated with this system. Similarly, at time if I had to do this for my control volume, then this would be equal to my CV, and this time is a beta rho dV. So which volume I integrate over ends up defining what extensive quantity you are calculating. So here B system refers to the total amount of B in the system, and BCV refers to the total amount of B in the control volume. Okay. Now at time t, the two are coincident, right? That's what we have drawn. The system and the control volume have coincided with each other. So I can write my B system at time t is equal to my BCV at time t. Okay, these are obviously functions of time, right? So these are functions of time. So here at time t, these two quantities are equal. Okay, but at time t plus delta t, these two are no longer coincident with each other. So in this particular case, my beta system at t plus delta t is not equal to my CV t plus delta t, right? Moreover, the thing is, the system, so by the way, in general, your B might itself be changing with time, capital B. So also, I'll just make a note here, also B system t plus delta t is not necessarily equal to B system at t. Okay, and why that is so, we'll see when we do examples. Right now I'm just asking you to sort of guess that there is, or basically believe that there is some beta and then there is some capital B, and we are not ascribing specific values or specific quantities to them. We're just saying it's some transportable property. So it might be a little bit abstract for you to look right now, but believe me, when we come down to looking at some of the problems, it will become far clear, much clearer to you. Okay, so our problem now is that this is not true. Okay, but what is, okay, but of course we want to, let's say, calculate BCV t plus delta t. Okay, we know that it is not equal to B system t plus delta t. That is because they have moved out, right? But what has really happened? Since it has moved out, it means that since they are not coincident, some new B might have entered my control volume at t plus delta t, and some B might have even left my control volume at t plus delta t, right? But think of it, that these three together, okay, they will have to add up. So if I have to write this B out t plus delta t minus, okay, so plus, sorry, t plus delta t. So these two are not equal, because by having moved out, the system by having moved out has let some flux out and some flux in. So if I do my math like this now, I will be able to account for the total transportable B in my control volume at t plus delta t. Okay. So now we'll just do some algebra. Once we have here, we will do, we will just a second, sorry, it's t plus delta t minus b system t. Okay, I'm just going to subtract this b system from both sides and divide by delta t, and what will I have on this side? I will have b system t plus delta t minus b system. See, this side is already looking nice. This is obviously going to transform into a derivative. Sorry, just this is b out t plus delta t plus b in t plus delta t by delta t. Okay. But we know that this quantity is equal to bcv, right? So I can actually change this to bcv and then take the limit. So take the limit delta t tending to 0. Okay, but before I do that, I need to do one more thing. Okay, okay. So this side will transform nicely. Okay, if you do this, then what can I write this side as? And this will become equal to dB, the derivative of this, the time derivative. Similarly, this quantity, if I do the if I take the limit, this will become my dB system by dt. Okay, but these things have not been resolved yet because this is some other quantity. Okay, for this to realize, okay, now b in at t is equal to b out at t equal to 0. So if you add a b out here and a b in term here, then and a subtract a term here, then you can convert these into time derivatives as well, and you will end up with dB system, sorry, system by dt minus dB. Okay, nice and simple. So now these quantities, can we start replacing this with these integrals that we have? Okay, so I'm just going to replace it with that. So this will now become, this should become ddt. Okay, so this is okay, I'm just going to write the integral first. So ddt of integral over the control volume for beta rho dv is equal to ddt over the control system, or what yeah, earlier I was what did I write here? Just one second, I'm just going to check. V system. Okay, so we'll just keep that lingo. beta rho dv minus this db out dt minus plus db in. Okay, sorry, this place has become quite crowded. Okay, just going to simplify this a little bit further. So I'm going to bring the system on my left hand side. So I have beta rho dv, okay, and this is equal to ddt of integral cv beta rho dv, okay, plus d b, this is b out minus b in by dt. Okay, now what is this particular term right here? This term represents the net rate at which B is leaving the control volume through the control surface, right? So this is actually the net flux into or out of the control volume. How can you calculate that? So if you wanted to calculate that, let's say that the fluid velocity out of the control volume through the surface, let's say you have, in my case, let's say you have the surface, so this is we have a surface element dA, and then you'll have a relative velocity of the fluid moving out of the control volume, right? So then the dot product of these two will give you the dot product of the relative velocity with the normal will give you the rate at which there is an outflux, and integrated obviously over the entire thing. So okay, so this represents my flux out of CV through control surface, right? Okay. So in order to calculate this, what we have to do is the flux out is related to, it says, you know, the relative velocity with respect to the surface, the unit normal at the surface, right? But so this dq amount that is leaving, so the volume, if dq is the volumetric flow rate through surface, through dA, through an infinitesimal surface dA, then my dq is given by my u dot producted with my area, right? This gives me the net volumetric flux out of the control volume. Okay. So if I have to calculate my dB out minus B in dt, then it would be simply equal to my integral over the control surface of beta rho. Now this is dq, and we have just written what dq is, so I could just go ahead and replace it with this form. So if you combine everything, okay, so combine this, okay, so now just go ahead and replace in this particular equation, then what will happen? Okay, then I can replace this with my integral over my control surface with beta rho u relative dot dA. Right? Okay, and there's only one more thing here, and that is, see, this is, I'm following a system of particles. Okay, so if I want to do a time derivative here, I need to actually use the material derivative. Some books keep this, some books keep it in DDT format. It doesn't matter. As I said, told you before, this is just a mnemonic. It is supposed to remind you how to take this derivative, that's all. And if you remember, then that's not a problem at all. So this term right here, okay, this term, this now represents is the rate of increase of B within the system. And what this equation is saying is that this rate is equal to this quantity, which, okay, maybe I'll just use a different color, that will be easier. Just a second, let me see. Okay, I have not used this green here, so maybe I'll use this. This is now, okay, I'm running out of space, so I'm just sort of cramping things here. Is the rate of increase of B within my control volume. And this final quantity, let's say you use this, this is my rate at which B leaves the control volume to the CS. That's already written, so I don't need to write that. So I've already written it, flux out of the control surface. This makes sense, right? The net rate of change within the system is related to that of the net rate of change inside the control volume along with the control surface. And this equation right here, this is our very important equation, and this is called the Reynolds transport theorem. Okay, so this is going to be a very, very important equation for us, and I want to make sure that you understand why this equation is very important. So let's do one thing, and let's go ahead. Okay, so we'll come back to the Leibniz theorem part in a bit, but I just want to give you an example of why we are doing this, so that you have some idea of what this is relevant for. Okay, so we have been able to derive this equation. Okay, by the way, just one more thing. Okay, quickly clarify one thing here, and this is, this relative velocity is basically my velocity of my system minus my velocity of my control volume, or my control surface, sorry. This is actually, sorry, this will be control surface. Okay, so this is the relative volume of the fluid relative to the control volume. Obviously it makes sense, right? So if your control surface itself is moving along with the fluid, then there would have been no point having a relative velocity. So if if uh, if control volume is fixed in space and not moving or deforming. Okay, so because the control volume is in the hands of the observer can choose to either move it or deform it. But if you not doing that, if the control volume is fixed in space, then this quantity is equal to 0, and url is obviously then just equal to the velocity of the material. Okay, so this is an important issue right here. Okay, so we have looked at the Reynolds transport theorem, but the question is, why is this equation important and what can we do with it? Okay, so my question is, what is this beta that we've been talking about? So we have been writing everything in terms of something called capital B, and then which we called some transportable property. Remember right here, let B be a transportable property. But then we can, and beta was the specific form of that, and then we converted. So we started off writing the equation in terms of the capital B, and then once we did our mathematics, then what we found is the final Reynolds transport theorem is in terms of my quantity beta. Okay, so consider the case where my beta is going to be equal to 1. If my beta is 1, let us copy this equation over there. That means that the time derivative of rho dV, and this is your volume system. Sorry, it's always mess up the y. This is the volume of system. So this is my LHS, right? What is this quantity? What is integral of rho dV? Just give a minute. Think about it. This is nothing but the mass of the system. So when we put beta equal to 1, the left hand side becomes the time derivative of the mass of the system, and that we are taking ddt implies that we are using the rate of change as we follow the system. And what do we know about the mass of a system? Well, the conservation of mass principle. So conservation of mass says that LHS should be 0. So this entire quantity right here, this quantity has to be equal to I'm just going to erase this. This quantity has to be equal to 0. So what does this imply? This implies, if I were to write the control volume part, then my ddt of integral, my beta is now 1, so this is my CV, this is rho dV, right, plus integral of the control surface rho u relative to dA is equal to 0. What a beautiful equation right here. And this is basically the statement of conservation of mass for a control volume. So this is your conservation of mass for your control volume. Now we are this part is not there in chapter 3. This is sort of chapter 4 of the book. So but I thought it's easier to explain if I were explaining why we are doing this in one lecture. Otherwise it just seems like a lot of abstract mathematics with no relevance to things. So and I somehow have this feeling that that's not a very useful method of learning things. So now this choosing different betas will lead me to different properties, and that will help me relate this important Reynolds transport theorem with important conservation laws. Okay, good. So to recap, okay, some important control volume is decided by the observer. It can be anything you want, but you have to choose the right control volume. And a lot of times in fluid mechanical problems, choosing the right control volume is the key to solving the problem, right? It's maybe, I mean, how do I, what other analogy can I draw? It's almost like, it's almost like in solving ODEs, guessing a good solution is the key to solving the equation itself. So it's almost like that. The control volume is up to the observer, but once you decide the proper one, you can understand it might be the key to solving the problem. So be careful in choosing or formulating your control volume. Okay. Keep track of your control surface. Your control surface. Okay. And if you are doing this problem, you must make sure that you understand or integrate properly over the control surface, because this integral is the key. Okay. So overall, this represents a very nice Reynolds transport theorem represents a very nice integral tool for dealing with fluid mechanical problems. Okay. There's obviously going to be when we come to the Navier-Stokes, we are going to see the differential formulations that are extremely relevant to fluid mechanics, but this is a very nice integral approach to things. Okay, so I'll just stop this recording and I'll start the other one almost immediately right now.